In this session, we're going to revisit the correlation coefficient, and we're going to look at it in a little different way. We're not going to use a data set. We're actually going to describe a process and then derive the correlation coefficient for that process. And what we want you to get from this is, again, a deeper understanding of how the correlation coefficient squared measures the percent of variation explained. So here's where we're going. By the end of this lecture, I'm going to describe a little experiment with you, and you're going to be able to tell me what the R squared for that experiment would be. In other words, what percent of variation would be explained by a variable that I give you. The experiment will involve rolling dice. So I hope it's a little bit fun, and I hope it's deepened your understanding of R squared. Okay, here's just a little bit of background information. We're going to be talking about rolling dice. So let's talk about what happens when you roll a single die. You are equally likely to get the numbers 1, 2, 3, 4, 5, or 6. So this would be a histogram that you would get, let's say, if you rolled a single die 1,000,000 times, and if it were a fair die. The average for those rolls would be 3.5, the number right in the middle. And we won't go into how I happen to know this, but the standard deviation would be 1.71, and the variance would be the square of that, or 2.92. Those are two pieces of information that we're going to be using. Okay, here's the prediction problem that we're going to be working with. Let's pretend that you have two dice, and you roll one of them and observe what happens, and then you roll the other one and observe, and you add those two numbers together, and that's the outcome of your experiment. So you want to be able to predict that before it happens. So with no other information, the best prediction you can come up with is a 7, because on average each of the dice will roll 3.5. If you were to pretend that you did that experiment 1,000,000 times, the average of those 1,000,000 rolls would be very close to 7. The variance would be 5.83, and the standard deviation would be 2.42. You don't have to know how I got that. That's is something that you derive using probability theory. And the histogram of those two dice rolls, or the sum of those two dice rolls, looks like the one shown here. And you can see that the more extreme values happen less frequently because there are fewer ways to roll a 2. There's only one way to roll a 2. Each die has to roll a 1. Then there are, say, to roll a 7, in which you could roll a 1 and a 6, or a 2 and a 5, and so forth. So we know for this particular experiment what our prediction would be before each experiment would be, and how big our error would tend to be over time. And what we're going to do is to say, let's pretend that we have some additional information, and that additional information is we get to roll the first die and observe what happens, and then we have to predict the sum. And obviously that's going to improve our prediction, and we can translate that improvement into a value of R squared. So here's the new situation that we would have is we roll the first die, and then we make a forecast of what the sum is going to be. And obviously we're going to do better. For example, if the first die roll is a 1, we know that the sum is going to be somewhere between 2 and 7. Whereas before, when we didn't know the first roll, all we knew is that the sum would be somewhere between 2 and 12. So R squared is a measure of how much improvement that we will get as a result of knowing that first roll. And R squared will be the correlation square the correlation between the first roll and the sum, and that's what we're going to talk about. We can actually write a prediction formula that says if I want to predict the sum, given that I know the first roll, all I need to do is to take the first roll and add 3.5 to it, and that line shows that prediction formula. So the contrast is going to be, if I didn't know the first roll, my prediction would be 7, and I'd have a certain size error. In this situation, I condition the prediction I make based on the first roll, and I'm going to get a smaller error than before. R squared is going to tell us how much improvement we get in that prediction error as a result of knowing the first roll, and that R squared will be the square of the correlation between the first roll and the sum. Let's take a specific example and look at it a little differently. Pretend the first roll is a 1, and you know that, and now you want to make a prediction of what the sum is going to be. You know that the range of that sum now will be from 2 to 7, and you know that each of those will be equally likely based on the equally likely outcome of 1 through 6 on the second roll. So your average for your prediction is 4.5, the one you already have, plus 3.5 as an average on the second roll. And the variance in the standard deviation will be exactly the same as the variance in standard deviation of a single roll of the die. So things have gotten a lot better in terms of your ability to predict what the sum is going to be now that you know the first roll is a 1. And now I can look at all of the possibilities, if the first roll is a 1 or the first roll is a 2 or a 3 or whatever, and I get a different average for my histogram based on what the first roll is, but the range is the same width and the standard deviation is the same and the variance is the same. So now we can talk about R squared, but let's review what information we have. If I'm predicting the sum before I know anything except the fact that I'm going to roll 2 dice, the variance of my prediction is going to be 5.83. That's when I'm predicting an outcome of 7. But if I get to observe the first roll and then make a prediction, the variance of my prediction error is 2.92. I've shown the diagram there one particular case, but the variance would be the same if the first roll was 1, 2, 3, 4, 5, 6. By what fraction does the variance of the prediction error improve when I know the roll on the first die? Well, originally the variance was 5.83. If I know the roll of the first die, the variance is 2.92. So if I take the ratio of those, the improvement ratio is 0.5. So the variance is now half what it was originally. We are now going to ask the question in a way that defines the R squared between the first roll and the sum. And the question would be, what percent of the variation, or what fraction of the variation in the sum is explained by the first roll? And the answer is 1 minus 1/2, or 0.5. Now that's not rocket science, but I hope it's intuitive. Each of the die rolls contribute equally to the sum, so you would guess that the fraction of the variation explained by one of them is 1/2. That's really all that R squared is telling you. Now, translate that into a real world problem. If the R squared between the square foot of a house and the price of the house is 0.67, that says that 2/3 of the variation in the house price is explained by square feet. We haven't even mentioned R. We've only talked about R squared. But I think you can also guess that r would have to be the positive square root of r squared, since the relationship between the first roll and the sum is positive. So in this particular case, r is going to be 0.71. So in the future, if you were to do a correlation and got an r of 0.71, that would remind you that, oh, this variable explains half of the variation in whatever it is I'm predicting. In the previous example, the ratio of the variances was 1/2, and then r squared, which is 1 minus that ratio, also came out to be 1/2, so that could be confusing. So we're going to do another little thought experiment here, and this time we don't have to go into all the gory details since you understand what we're trying to do. Let's pretend in this experiment we're going to roll 3 dice and sum. And we again want to compute the correlation coefficient between the first die roll and the sum of all 3 of them. And the question that we would start with, well, what would r squared be? And you know enough now to know immediately what that should be, because we got 3 dice and they're each contributing equally to the sum. So if you're asking what is r squared, how much of the variation or how much of the variance does the first roll account for? And I think you have already guessed that. So if not, think about it for a second longer and then we'll talk about it. That's right, r squared is going to be 1/3, because the first roll explains 1/3 of the variation in the sum. If I were to tell you that the overall variance of the sum of 3 dice is 8.75, that's what it actually happens to be. You should be able to now answer what would be the variance of the prediction once the first die roll is known. The reason you should know that is you know that that first roll is going to explain 1/3 of the variance, and the other 2/3 is what is going to be left. Okay, here's the math, and it turns out that the first roll is going to explain 1/3 of the variance. So we're going to have 2/3 of it left. And so the new variance would be 2/3 of 8.75, or 5.83, which it's not a coincidence that that happens to also be the variance that you get when you sum 2. And then the next question would be, what is r? And the only thing you have to think about here, you already know r squared. The only thing you have to think about here is r positive or negative. Does the sum go up when the first roll goes up, or does it go down? So I think we've got that one under control. And r comes out to be 0.5773. So you kind of got to keep that in the back of your mind always, because in Excel, when you look at the correlation between variables, it will always give you r, and here, for example, r is almost 0.6, and what that's really telling you is that the relationship explains about 1/3 of the variation, not 0.6 of the variation. I'm going to define another little experiment here, which sounds more complicated. It's actually the same thing in disguise. Let's pretend that I roll 3 dice, and then I define my outcome as the sum of the second and the third roll minus the first roll. And let's pretend also that I ask you to tell me what the correlation coefficient and the square of the correlation coefficient will be between the first roll and that outcome that I'm computing. Nothing's really changed from the previous except for one little thing, and that is the sign of the correlation coefficient. I still have 3 dice that I'm rolling, and each is contributing equally to the outcome of the experiment, It's only that one of them is contributing in a negative way by being subtracted, and the other two are contributing in a positive way by being added. So since they all three are contributing equally, we know that the r squared for the first one is going to be 1/3 again. The only difference is we know that as the first roll increases, the predicted outcome decreases. So the relationship will be negative, so the sign that we put on R will be negative. And so here is the answer. Now here's what you should be able to do after having worked through all of these things. You should be able to determine, if you were to roll 4 dice, what the correlation coefficient would be between the roll of the first die and the sum of the 4. If you can do that, you've deepened your understanding of what we mean by r squared. And that's all for this session, and I hope this helped you gain a little better feel for what r and r squared are telling you.